the Haber process. Now, we've come across this before when we were talking about reversible reactions last year. Remember dynamic equilibrium and all that stuff? Okay, so basically, if you mix these two things together, they start to make ammonia. The ammonia's concentration increases and the ammonia starts to break up and to reform nitrogen and hydrogen. So you essentially establish an equilibrium, the dynamic equilibrium, dynamic because the forward and reverse reactions continue to happen, but equilibrium because they happen at the same state, at the same rate, so the quantities at equilibrium of these reactants and this product or these products is constant. So dynamic because the forward reaction and the reverse reaction continue at the same rate, and equilibrium because the amounts of reactants and the amounts of products are constant. Not the same, but constant. Okay? You might have lots of reactants and very little product, but that's an equilibrium that's set up. The energy change for this reaction, delta H, is -92. So the forward reaction is exothermic, which means the reverse reaction is endothermic. So a lot of revision there, isn't there? The raw materials for this process, well, nitrogen is very easy to obtain because the air is 78% of it, remember? So if I burn some hydrogen in air, the hydrogen will react with the oxygen in the air, and nitrogen remains. So we've got nitrogen. Hydrogen we get from steam reformation of methane. We could have got it from electrolysis. There are other sources, but generally the most abundant source is from steam reformation of methane. So we take methane, natural gas, and we heat it with steam, and what happens is the methane reforms to give carbon monoxide and lots of hydrogen. Okay, and this hydrogen, we can use it in the Haber process. So methane, natural gas, gives us the hydrogen for the Haber process. This is what the whole process looks like. We put nitrogen and hydrogen in here. We've got a catalyst here. They react and they form ammonia. Because of the high pressure, which we'll talk about in a minute, the ammonia is condensed to form a liquid and can be tapped off. Any unreacted nitrogen and hydrogen can go back around and can react again. Okay? The coolant here, this condenser, helps the ammonia to condense. Don't worry about that. Now, we've got to talk about optimum conditions. The optimum conditions refer to the best temperature and pressure to make as much ammonia as possible, and therefore profit. So the optimum conditions in industry for this reaction are a high pressure that forces this equilibrium to the right. Remember Le Chatelier's principle, LCP, Le Chatelier's principle. If I increase the pressure here, then the reaction will shift in the direction of fewer moles or fewer molecules in order to decrease the pressure again. Okay, so high pressure, 200 atmospheres. You need to learn these numbers. 200 atmospheres. Moderate temperatures. Now, because the forward reaction is exothermic, then it would be best to run the reaction at a low temperature to encourage the reaction to go forward and to increase the temperature again. But if we do it at too low a temperature, the reaction rate is very low. Reaction is very slow. So we do it at a moderate temperature, 450 degrees C. It leads to a good reaction rate, and then we constantly remove the ammonia. To make this reaction happen better, we use a catalyst, which are beds of iron. So there's an iron catalyst in here. Again, you need to remember 200 atmospheres, 450 degrees C, and the catalyst is iron. Liquid ammonia is constantly removed. Again, if you take this out, then what happens is the equilibrium says, hang on a second, you're not taking my ammonia away, I'm going to make some more, and it shifts to the right. Okay, so this is good revision of equilibria, dynamic equilibrium. And this is an actual example of when we use it in industry. Okay, so reactants in, react with the iron. The ammonia that's produced is condensed with the pressure, and also there'll be a coolant here. Any unreacted nitrogen and hydrogen are recycled, and the whole thing just keeps going 24/7. Okay, try the questions on the pages indicated. Let's have a look at the uses of ammonia. Ammonia can be used to make nitric acid, and nitric acid is very important in making polymers like nylon and explosives. It's used to clean in the household and in industry. It's very good at cleaning. It's a good solvent. It's used to make fertilizers, and this is its major use. Because of the nitrogen present, then they produce really good fertilizers with lots of nitrogen. We'll talk about that in a second. Ammonium salts are produced by reacting ammonia with acids. So, for example, if I react ammonia with nitric acid, I get ammonium nitrate. Write these equations down. If I react ammonia with sulfuric acid, I get ammonium sulfate. Careful with the balancing. And if I react ammonia with, for example, hydrochloric acid, I would get ammonium chloride. We don't really use ammonium chloride as a fertilizer. Ammonia is extremely soluble in water because of the strong bonds that it forms with water molecules. Also, there's a reaction that takes place. Ammonia reacts with water to produce ammonium ions, NH4+, that plus really should be on the other side, and the hydroxide ions, that minus should be on the other side. And this is what makes ammonia solution, it makes it alkaline, the presence of hydroxide ions. Okay, so this also helps ammonia to be very soluble in water, which you can see. Have a look at that demonstration, which is online. You can see the demonstration of the fountain experiment. Okay, and one little word about fertilizers. They have NPK values. So we want a fertilizer with nitrogen, which causes the production of green foliage, leaves, etc. Phosphorus for roots and blooms, for flowers, and potassium for overall plant health. The classic fertilizers are indicated here. Try writing the formulae for these three fertilizers. Phosphate ion is PO4 3-. Have a go. PO4 3-. There you go. There are the formulae for those fertilizers. And this is the production. Ammonia reacted with phosphoric acid gives me ammonium phosphate. So in this you've got ammonia, sorry, you've got nitrogen and phosphorus. Here you've got potassium, here you've got nitrogen. Okay. Typically, fertilizers, a bag of fertilizer would combine these compounds. So you wouldn't be buying one thing. You would combine different compounds so that you've got an N, a P, and a K in the fertilizer. We can test for ammonium ions. If you think back to testing for ions, we probably mentioned it back then, but we'll talk about it now. If I've got an ammonium ion and I add some sodium hydroxide and I heat it, if I warm it in a test tube, then what happens is ammonia gas is produced. So I'll take a little bit of my solid or solution of suspected ammonium ions, add some sodium hydroxide and warm it. And then I test for any gas produced. If the damp red litmus paper, the damp red litmus paper at the neck of the test tube, if it turns blue, then it shows that an alkaline gas was produced, which is most likely ammonia. So this is the test for ammonium ions. Sodium hydroxide, warm it, and at the neck of the test tube, damp red litmus paper turns blue. One last little thing before we finish. Good reminder of dot and cross diagrams here. Ammonia molecules, you should be able to draw their dot and cross diagram. Nitrogen and 3 hydrogens, so have a go. And ammonium ions are an ammonia molecule with a H plus added. So what happens is a H plus comes along and grabs a share of these 2 electrons. It doesn't bring anything to the table. So that hydrogen comes along, it's a H plus hydrogen ion, and it just takes the 2 electrons from the ammonia molecule to make ammonium ions, NH4 plus. Sneaky, no? And that's called a dative covalent bond. They're not really required for IGCSE, but it's worth knowing that sometimes that happens. Something comes along and takes a share of some electrons without bringing any electrons with it. Right, have a look at the pages indicated and answer the questions about fertilizers and the uses of fertilizers and ammonium salts.